Oh, thank you, Vishal. So let me pick up where we were last time. So I told you kind of quickly at the end how to compute Cauchy integrals on the unit circle. And that was basically using the fast Fourier transform to interpolate a function on the unit circle with Laurent monomials. And then once you have that representation, you can apply the Cauchy integral directly to that series. And then if you're doing it on the real axis, you first take your function on the real axis, you map it to a function on the unit circle, and then you apply that method and you unwind everything. Okay, so before I go on to kind of a bit more theoretical stuff that allow me to truly introduce a Riemann-Hilbert problem precisely, let's talk about what we would do on the interval -1, 1. Integrals on -1, 1. Okay, so first thing I'm going to do is define tk of s, which is cosine of k, cosine inverse of s. So this is a so-called Chebyshev polynomial. Chebyshev. And this is of the first kind, but it won't, that doesn't really matter. Right, so it's a non-trivial fact that this is actually a kth degree polynomial in S. Okay, and so how do you compute? Our goal is to compute this quantity. We want to compute this. I want to compute it for any z in the complex plane. And then I also want to be able to compute boundary values back to the interval -1, 1. Okay? So to do this, the first thing you have to do is you take f, function on -1, 1, and you approximate it series, say j equals 1 to, we'll use k. That k equals 1 to n ck tk of s. And a good question is how? Right, so these, based on this representation, you see cosines, so you can actually take this function to do this approximation. You take this function and you can map it to a even function on minus pi pi. And then it's an even function on minus pi pi. You use the fast Fourier transform, and that actually gives you a cosine series representation. And then you map it back, and you get exactly this. And so the actual how is discrete cosine transform. Okay, so that's something I'm just going to kind of sweep under the rug and say we have this tool that, given a function on -1, 1, that's sufficiently nice, I can compute these coefficients ck in a very easy way. There's just a numerical algorithm out there that does it for me. Okay. Then I'm going to actually take a slightly modified approach. So I'll take this series, and this actually just simplifies the discussion. It's not necessary. So we take k goes from 0 to n, get new coefficients, and then I'm going to have a new basis. And this new basis is very simply expressed in terms of the old. We just have phi 0 is equal to t0, phi 1 is equal to t1, and then phi k is equal to tk minus 2 for k bigger than or equal to 2. So why do I do that? Well, these guys are all equal to either plus or minus 1 at the endpoints -1 and 1. Right? You can actually see it from this. So they don't vanish at the endpoints of the interval. So when I take a Cauchy integral of one of these guys, I'm going to get a logarithmic singularity from the endpoints. All of these vanish at both the left and the right endpoint. And it's really properties of these Chebyshev polynomials. So this is true for k big 2. So that's an important property. These guys, of course, don't. So T0 is actually just 1, and T1 is x. T1 of s is s, just a linear, simplest linear function. So when I take Cauchy integrals of these guys, I'll get logarithmic singularities that are unbounded. I'll still have logarithmic singularities hidden, but they'll be multiplied by some sort of polynomial that will make it a bounded thing at the endpoints. Okay, you don't have to do this, but it just kind of it isolates your unboundedness in 2 basis functions, and everything else becomes bounded when you take a Cauchy integral. Okay, so we have our function. We use a DCT to get this. We take this and we convert it, and these coefficients are really easy to compute from this definition. You just have to iterate through and modify some things. Okay. And then so she and Olver has a nice formula and method to compute the Cauchy integrals of these things. It's also in a different form in our book, so I'll add that as a reference. Formulae for the following. So you want to be able to compute the Cauchy integral of all of these bases. And Ci minus. So there's formulas out there, and I'm not going to even try to write them. They're in terms of hypergeometric series. And on the interval, it's simpler. These are a bit simpler, but this one is more complicated. Because you actually have to rewrite everything in terms of a series that decays at infinity, and there's some technical bits that you have to deal with. But you should be a little bit worried about these, especially when j is 0 and j is 1. What do I mean by these boundary values? And so this is a bit of abusive notation, but what we've decided that it's kind of a nice way. So this is for j equals 0 and 1. I need to do this. If I look at my boundary values, I'll say s plus, and this is just notation. All right, so this is really saying I'm at s and I'm approaching from some angle phi. And I'll just put a 0 here, u to the I phi. Okay, and so there is some restriction on the angle, and I don't really want to spend too much time on it. I just want to kind of give you a rough flavor of what's going on. So you have your boundary values, and you really just define this to mean, in the interval, I have C plus as C minus because of the Holder discussion we had before. And so we don't even worry about what this means on the interval, you just get that. On the endpoint, so and all of this is discussed in here. I have to define some sort of regularization of the Cauchy integral at the endpoints. Yeah, so this should be set. Yes. And what this really is so you compute your Cauchy integral, you have a logarithmic singularity. When you have your logarithm, you have log of the modulus, and then you have your phase. And so what this really does is subtracts off log of the modulus, but leaves the phase. So you actually get a different value, but it's a finite value as you approach from different directions. And this is particularly important. I'm doing something like this. And I have a function, say, defined on this contour, I compute its Cauchy integral, and I want to define its limit at the corner. And I need to keep the angle, and I need a mechanism to keep the angle, track of the angle. Okay, so this is all really just to say that there's a bookkeeping method to deal with Cauchy integrals at endpoints and making sure that you always compute with finite values. Because if I left the logarithm in there, I'd get some sort of plus or minus infinity, and then I have lost all information. And I'll say a little bit more about what that is and how you work with it later, but I'm not going to define it. It's just the way to think of it is a regularization. And it only gives you the correct value if you're working with the correct class of functions. But for any class of functions or any of these, it will give you a finite value, but it might not actually be the value of the Cauchy integral. Okay. Right, so then this would actually then be 3 in terms of what I'm talking about. So we have this, we expand it, we compute these new coefficients, we open up, yes? Yeah, so there's things, mainly what changes is when I say correct class of functions, that changes based on whether this is this way or this is this way. Yeah, and I should get to defining that today. Yes? Okay, yes, that's bad. Let's call this theta. Thank you. Yeah. Bad notation. And this, I'm missing a J. All right. So we have our function on -1, 1. We use our DCT to expand in a series. Then we convert our series to a modified 1, and then we open up this, we have these formulas, we implement the formulas, and we compute the Cauchy integral, term by term. Okay? And so a little bit simplified story, but that's really effectively what's going on. But now let's think about gamma, Cauchy integrals on gamma, and gamma will be given by a parameterization, and t is in -1, 1. All right, so just, well, it's a Mobius transformation, but it's just a simple linear function. Right, so that's my new, now I want to do the Cauchy integral. And so for those of you who were in the discussion section yesterday, I showed you how you can compute, there's this important fact, that C gamma f of z is, so this little gamma maps me from unit interval to the curve. So I can write this as, right? So now this will be a function on -1, 1, so I don't want to do this, I want to do this. And then I apply the Cauchy integral to this function, and then I evaluate at, right, so I map my function, compute the Cauchy integral, and then evaluate at some other point. And that's just a change of variables. It's very, very elementary to show this. Right, so then I can treat any contour gamma, once I have this machinery, I can treat any contour gamma that's a linear mapping of -1, 1 by such a transformation. So such a contour, I just, there's kind of this -1, 1 that's hiding around in the background, and I have different transformations. And then I can compute the Cauchy integral on some combination. And then this really comes into account just at the intersection points. Okay. Okay, so that is a kind of just a sketch of how you go about computing Cauchy integrals on general curves. So now I'm going to work for a little while to get a very precise definition of what a Riemann-Hilbert problem is. I've given you Riemann-Hilbert problems with 4 conditions, but I'm going to relax them. I'm going to give you a new definition, or really a precise definition, which just leads, we do a lot of work there, but it leads very naturally to an integral equation, and that's my whole goal for computation. Solving integral equations is somehow a well-known thing. Okay, so here's gamma be a contour. Right, so it's a finite union of arcs and curves. And define omega to be C take away gamma. And then we assume the following. So these assumptions, so gamma is a contour. We will also assume that it's Carlson. All right, we won't do anything that's not. Everything will end up being piecewise smooth, but even the Carlson discussion is needed to understand this because it's not smooth at this point. So you do actually need that full theory or something close to it. Okay, so we assume, and what these assumptions will be summarized by saying gamma is admissible. That the first thing is gamma is oriented in such a way that each D, and when I use this notation, this means connected component. So that each connected component of omega has either a positively or negatively oriented boundary. Okay, and so I'll draw a picture in a second. This is really a consequence of this, but so we decompose this into two disjoint pieces, where D being a connected component of this, respectively for connected component of this, as positively or respectively negatively oriented boundary. Okay, so what do I mean by this? So best example is just, let's think of our contour, not even draw arrows, contour being the real and imaginary axes. And so what this is really saying is I look at all the connected components and I can color them white or black. And if you think about it, right, so I want to, everything I have to orient the contour in such a way that right, so this, I have to have a single orientation on the boundary, so that would be omega plus. I can't switch this one without switching that one. That region has to have the same orientation on the boundary. And then, okay, this one, I have to have the same orientation, so that forces this to be that way. And then this lies to the right, so this is omega minus. And then that also then forces this guy to have this orientation. This is omega plus. This is omega minus. Right, so I just look at each component and I have a given orientation on the boundary. Right, so if I had the real line, I cannot have this part oriented that way and this part oriented that way. That does not work, right? So I could divide the real line into this contour, this curve, or I should say this arc, and orient this one this way, and that one that way. Okay. Right. And so it's really a kind of a statement that you can take the connected components and you can color them white or black, and a black region will never border up against another black region, because as you jump over that contour, the boundary switches orientation. Right? And any curve that we will encounter that doesn't satisfy these conditions, it'll be clear that we can augment it with additional curves, change orientation so that it does. So it's really kind of a technical condition that just helps the bookkeeping, but it's in no way fundamental to the to proceeding. Okay. So
I have a question.
yes.
Just so that I understand. In your example, suppose I have the real line and just the imaginary axis in the upper half plane.
Right, so you're saying, what if we have this? Or I won't even worry about orientation.
Yeah.
Right? Okay, so the theory says that for the lower half plane, we have to have a consistent orientation. And then this one says that this has to be that way, but then this doesn't work. Right? So then what I would have to do is draw an additional contour, augment it, and now that works. And so then if you're thinking about the theory of Cauchy integrals and you really only care on this, I don't know, this upside down t contour, then what you say is, well, okay, I'll do Cauchy integrals on the full thing, but I'll just restrict to the class of functions that are 0 on there. And then the theory goes through for those classes. You deduce the theory for those classes. Okay. So with kind of putting that in the back of our minds for what's going to be going on, we'll talk about Hardy spaces. And 2 references for this. So there's Duran's book from 1970. And then there's also some lecture notes from Jin Zhou. These are lectures at MSRI. These are not easy to find. So I believe I have a digital copy of them. So if you're interested, let me know and I can get that. There is some materials on the MSRI website, but the full notes I don't think they're up there. Okay, so talk about Hardy spaces, and we'll first start with the upper half plane. We say that F is in E2, so I'm going to do everything L2 based. There's generalizations to LP, but again, we won't go into that complexity. Okay, so F is in E2 of C plus of the upper half plane if F is analytic in C plus, and we have an estimate that the supremum over all R positive integrate over R. We take F and we shift it up by an amount R, if this is finite. Right, so it's an analytic function in the upper half plane that has some sort of uniform bound on L2 norms along lines. So I look at my function up, L2 norm, and that has to be uniformly bounded. So a good example, or a counterexample, I really should say example of a function that you might think is nice but is not in here is, say, e to the minus s squared. Right, so, or I should say z squared. It's thinking of its boundary values. Right, so this actually has nice boundary values on the real axis, and if I did this, it would be finite for this function. But, so all R positive, and as R goes to infinity, the L2 norm of this function along lines in the upper half plane goes to infinity, and you don't have that. And basically, the way to think about these functions, at least heuristically, is they're analytic functions in the upper half plane that decay like 1 over z at infinity. They're not exactly that, but that's kind of a good picture to have in your mind. So everything we've talked about I emphasize, we have a uniform 1 over z control on the function, or uniform 1 over z estimate on the function, and it's continuous up to the boundary. That's enough to guarantee this. So the error function in the right half plane, when I did the estimates for the Fourier transform example, that had those estimates in the upper half plane, so on. Okay. And then, so that's fairly classical, or is very classical. And the notation there is standard. Now the notation I'm going to use is absolutely my own. So then I will say that f is in E2 of R, right? So this I put in some open set in the complex plane. Now I'll talk about E2 of a contour. What does that mean? This is if f is analytic in C, take away the contour. F restricted to C plus is in E2. And I take F, I restrict it to C minus, and then I take it and I evaluate it at negative. So I really flip it to a function in the upper half plane. Then now this is a function in the upper half plane. I can talk about this being an E2 of C plus. Or equivalently, I could define the same thing with sup over all R negative and get analogous Hardy space in the lower half plane. So when I stick in a contour here, I really mean off the contour, we have all these open regions, these omegas, and in each omega, my function's in the appropriate Hardy space for that connected component. Okay, but I've only defined things for R. And so that's the next step. And this, for the sake of time, I'm not going to write out the full details. I'll just kind of say it in words. All right, so let me just do it by picture, because this will then fit with what's going on over there. Let's say this is my curve gamma, or my contour gamma. Okay, and then I have a region D here. So I'm thinking this is the full first quadrant. And now I want to define a Hardy space there. So you think of these as being their contours in the upper half plane that approach the boundary. And so what you actually do, is I start with a sequence of contours that grow in size. And so it should be not obvious that this would give me, so if I took the upper half plane and I took a sequence of rectangles that grew, and what I require is the supremum along this sequence of L2 norms over all these contours, that is finite. Right, so here I just did these contours that could approach the real axis or infinity. Or here I have this whole sequence of contours that expand out, and I require the same uniform bound on my norms along all those curves with respect to arc length. L2 norm with respect to arc length. Okay, and should not be at all obvious that if I do define things in that way, I get the same space of functions. Analytic functions up there that have a supremum over, as this grows, and I take the norm over all these growing contours, and that's finite, that I get the exact same class of functions. But you do. And then once you make that realization, you go over here and you say, okay, well then I'll just do the same thing. I'll take a sequence of contours that expand to the boundary, and I'll require my function to be analytic in the domain, and then have a uniformly bounded L2 norm on these curves as these curves expand to the boundary. And then that allows you to define the Hardy space on a general domain. Right, so I guess one way to think about it is the unit circle. You'd start with a point or a small circle in the middle, and then you'd take the supremum as your contour approaches the unit circle. It's the same idea, but you have to generalize it to different geometries. Okay. So this can be done. And I mean, this is probably the most technical part of the whole theory, is understanding the Hardy spaces. And then establishing, well, so okay, the L2 boundedness of the Cauchy operators is also extremely technical. But then this, along with these, let's see here. Okay, and so then, so I can do this. Let me just kind of think about, okay, I could do that. We have the same picture over there. And then I could look at, okay, functions analytic off of the contour that are in the Hardy space here, Hardy space here, Hardy space here, Hardy space here. Question?
Yeah. I could also take these unbounded lines and map them to the real line, and then by a change of coordinates. So there's another way to define Hardy spaces, yes, which is by domain transform.
Right. And so that one I don't want to do, because I don't want to map the unit circle to the real line or vice versa, because I don't want that extra singular bit in my change of variables. Because in the Cauchy integral, I don't have any extra rational term. I have to just work directly with the geometry that's in front of me. I can't map it. Well, I mean, you could map it, but you have to be careful of what the mappings have to have uniformly controlled derivatives and things like this. Okay. So then I can define D, I can define this, and then once I say, okay, my function is analytic off here, and for each connected component, it's in E2D, that lets me then go to, well, let's do this. You know, and it's the same way that I defined this for a contour, I can define this for a contour. Well, we want to make sure the contour satisfies those assumptions so that all, I mean, it's clear that we just go to these different connected components. Well, I mean, it doesn't actually have to, but we will enforce that it's admissible anyway. Okay. So we have some facts. So if gamma is admissible, this is one of the most important features. So I take my Cauchy operator, and I don't take boundary values. I take it and I map it to an analytic function. And I map all L2 functions on my contour. So now I get some space of analytic functions off the contour. Well, happily, that is just this space. It maps onto the Hardy space. So importantly, every element of the Hardy space is the L2 integral of some function. And that's like the most important reason we go through all of this construction. That will let us construct a singular integral equation. There's other nice facts we won't use so much, but are very useful in other places. So if I apply the plus operator, so I take a function on the contour, this, and then I apply it again, because of all of the geometric considerations, this is a projection. That the C plus operator is a projection. Then the C gamma minus is effectively the complementary projection. This one, so right, this was actually true just in the Carlson setting. I didn't actually write it up. Right, and then, I mean, it's really a consequence of all this, but and I should just be a little bit clearer that this one and the next one I write all require F in L2 of gamma. And then the last one really follows from these projections. C gamma plus, C gamma minus of F is 0. So they're projections, and you also have this important definiteness. Right? So if you have two functions, so what this actually says is this C plus is a boundary value of a Hardy space from the positive side of the contour of a function. You take a function there and you take its limit to the plus side, gives me this guy. And then I take one limit from the minus side. If those guys are equal, the only way they can be equal is if the function's actually 0. Okay. It's really saying you have an analytic continuation off, and then this is really giving you some sort of boundedness at infinity. It's a Liouville's theorem, like generalization, roughly. Okay, and now let's do something a little bit more concrete. Just an example. I kind of promised this, I think, in my first lecture. So f, which will be a function from C, take away R to C, we'll define it for Z not real as Z as that. Right, so this is clearly an analytic function off of R. If you work through the expansions, you'll see that f of z is uniformly order 1 over z. Just use the Taylor series for e to the 1 over z. Okay, and the limit as epsilon goes to 0 from, let's just write it this way, epsilon goes to 0 through positive values, f of s plus I epsilon, s being real, so now we're looking at a boundary value from above. This will be equal to the limit as epsilon goes to 0, f of s minus I epsilon. So now this is the boundary value from below. Right, so it should be clear from this that this being true is obvious for s not 0. It's an analytic function with an isolated singularity at 0, so the boundary values from above and below have to be the same. Okay, the only thing is left to check is s equals 0. Right, so, okay, this along the imaginary axis is oscillatory and bounded. So this goes to 0. Right, and then, okay, this goes to, so I get -1 for my limit from above and below. Okay, so it looks like I found a function analytic off the contour, decays at infinity, has limits from above and below that are equal. But if you go back and you check this condition, this will not hold. Right? Because we know actually if that happens, f has to be identically 0. That's really what this is saying. Well, this combined with this is what it's saying. Right? But f is not in the Hardy space. You can also just look at its boundary value and it blows up. What this is really saying here also, combined with it's really the fact that C plus and C minus have boundary values almost everywhere, it's really saying that every Hardy function is the Cauchy integral of its boundary values. Right? So that's you usually figure out your Cauchy integral formula. Okay, f of z is equal to the Cauchy integral around the curve, and you evaluate inside. If it's analytic inside and continuous up to the curve, that's true. This is a generalization of that, the generalization of Cauchy's integral. Question?
Yeah. So this for the real line. So if I take a function that's supported on the real line and I take its Fourier transform, and Paley-Wiener theorem says that I have an analytic function in the upper half plane.
Right.
right? So this is taking a function defined on the real line, taking its Fourier transform, or rather taking a function defined on the real line and splitting it into two halves. Right. One whose Fourier transform is analytic in the upper half plane, one whose Fourier transform is analytic in the lower half plane.
Yes.
Is that right?
So yeah, so the way to think about what this is, actually this is the Cauchy integral, is you take a function on the real line, L2 function, you take its Fourier transform, then you split it into a function minus infinity to 0, function 0 to infinity, and then you invert the Fourier transform individually for those two guys. And then one will be analytic upstairs, depending on how you define your Fourier transform. One will be analytic downstairs. Those that you're evaluating up and below are exactly the Cauchy integral. And then the boundary values give you the full Fourier transform. This minus that give you the full Fourier transform. And, well, actually, you actually do need to do minus one of them below. But yes, right. I mean, it's more, but it's more of a generalization of this idea to arbitrary contours. Yeah. Ah, yes, that's very important. Thank you. Yeah. Yeah. Maybe I'll emphasize my mistake. Yes. Very important. Yeah. Because otherwise, all the Riemann-Hilbert problems we've encountered, just in this case, would have non-unique solutions if this was a valid solution. But this also, based on how we set everything over there at the beginning, this does not have continuous boundary values. Because at the origin, actually, you take your boundary values, you look at the function you get, and it blows up at 0 because of this essential singularity. Because of this guy. I would say how you usually fail in terms of when you're doing the calculations. I mean, that's a tough question, how you usually fail. But, I mean, it's either growth at infinity or failure of some regularity of boundary values. I mean, those are really the two ways. Okay. Perfect. So now I can finally state what I mean by a Riemann-Hilbert problem. So, given an admissible contour gamma and a jump matrix, it could just be scalar like we've seen, but it doesn't have to be. G, which is defined, which is the given data. So it could jump matrix G, which takes values, complex n by n matrices. And then F will be another function which will be taking the contour to C n by m. So n and m are integers. They do not have to be equal. Okay, so these are the given data along with the contour gamma. And then the problem is to find a function phi, which will take C, take away gamma. To C, it will have the same dimensions as F. Analytic. And maybe I'll actually change the order from what I have in my notes. So we'll say that phi minus some constant. So I'll tell you what that is. Okay, so I'm looking for a function phi that once I subtract off a constant, it's in the Hardy space. So you should really think of the constant as being its behavior at infinity. Right, so when I write that, I mean component-wise. Yes. Such that phi plus of s, phi minus of s, g of s plus f of s for almost every s in gamma. Okay. So really, I mean, heuristically what I'm saying is I'm looking for a function phi, analytic off the contour, a matrix valued function that tends to the constant matrix C at infinity, and it satisfies this jump condition. So we're really, let's get our orientations right. All right, so on the contour, I have f and g given data, and then here's my plus and minus. So phi plus from this side, phi minus from this side. I should have phi plus equals phi minus g plus f. And then in quotation marks, the limit as z goes to infinity of phi of z is equal to c. You have to be, that's what this condition is capturing, but it actually doesn't mean that. To have, because you, yeah. It all, depending on which direction you go, and there's a lot of complications there. And your curves could kind of be meeting at infinity and so on. And so the main thing that I want to use this, so now we have this, let me simplify the setting a little bit. So that's the general problem, and what I'm going to do, you can easily do for that, for the general setting, but let's do a calculation where we set f is equal to 0, n equals m equals 2. I mean, I'm not going to really use that, but I just really want to think of things being square, and this is the case that we'll see later on. And C is the identity matrix. No, C. Yeah, what it tends to at infinity. Yeah, C. And well, yeah, we won't really make any assumptions on G. Okay, so I have my jump relation. I have then phi plus of S is equal to phi minus of S, G of S. Okay, and then how can I write phi? Right? So I want so we have this boundary value problem in the complex plane. I want to just reduce it to something that exists solely on the contour gamma. Right? So I basically reducing a two-dimensional problem to, so one complex dimension to real to a legitimately one-dimensional problem, just on the contour. Well, so I've made the assumption that, or defined, if I have a solution, it has to satisfy this. So phi has to be a Hardy space function plus a constant. So it has to be a Hardy space function plus the identity. Right? So that means that this guy has to be the Cauchy integral of some function. So this. So every Hardy space function is found by the Cauchy integral of some L2 function plus an identity. Yes, component-wise. Right. And really, to do everything well, I have to introduce, if I'm working with matrices, I have to introduce the matrix norm and make sure everything's consistent. But yeah, there's no real complication there. Okay. So now substitute. We know we have boundary values for U and L2, so we can substitute C gamma plus U of S plus I, C gamma minus U of S plus I, G of S. Okay, let's move this to the right-hand side, and I'm going to subtract this from both sides. So I'll move this over and subtract this from both sides. And so then I get minus C gamma U minus of S minus the identity. Okay. And so we know that this is just U. And let's see. I can combine this term with this term as a C U minus of S, G of S minus I identity. So that is this term and this term. And then the last part is that. So let's do this, move this over, minus equal. That's what I wanted. That's the most important fact for the numerical solution of Riemann-Hilbert problems, for doing anything computationally, or even actually doing rigorous asymptotics. It's based around this. All right, so this is a singular integral equation. For U. And once I solve that integral equation, I can show the associated operators invertible, I can solve the problem, that gets me U, and that gets me my solution. So this is really the boundary integral reformulation of a Riemann-Hilbert problem, so to speak. Okay, so you can do C equals 0 as long as F is not 0. So actually, let me, since I can't really go on to the next topic, let's kind of elaborate on that. So I can consider this problem in two ways. So, right, so I have this, so I'll summarize it. So it's phi plus S equals phi minus of S, G of S. And I'll, well, I could define a new function, call it psi, which is just phi minus I. And I can ask, okay, this guy is straight away in the Hardy space, so in a heuristic sense, it decays at infinity. Okay. Then we rewrite the jump condition for psi. So we get phi plus minus I phi minus of S, G of S minus I. And I write this as phi minus of S minus I. All right. And so then now I write everything in terms of psi. And now in this case, we actually have C equals 0. Right, so if you don't have it go to a constant at infinity, you could recast the problem by having it go to 0, but then you get a right-hand side function, basically.
Homogeneous problem with 0 boundary conditions and an inhomogeneous problem.
Yes, right. Absolutely. Mm-hmm. That's why I like to think what happens at infinity is the boundary condition. And then you have this, if you like the analogy to differential equations, that's your boundary condition. This is your differential equation. And then you either have an inhomogeneous term or you do not. Right. And then uniqueness boils down to, at least in this case, into having a solution, a non-trivial solution that satisfies this, but has C equals 0. Right? Having a non-trivial solution to your homogeneous problem. problem. So I can always add on a constant times that one, and I keep satisfying all of my required conditions. Okay, so it looks like I'm out of time, so I will stop there. So for the applications I'm going to do later from here on, F will always be 0. So I technically didn't need F, but if you want to see what we've already done fitting in this framework, you need F, because we had phi plus minus phi minus is equal to something. So that we had an inhomogeneous term. And then once we get to inverse scattering, we work with solutions of nonlinear PDEs, then it's necessarily G is necessarily a 2 by 2 matrix.